시작. 나는 프레스 눌러주겠다. 오케이.
잘 보이겠지?
네, 오늘 와주셔서 감사하고요. 오늘 그 톡을 해주실 분은 그 구글 리서치 유승현 박사님이고요. 저랑 도지한테 잠깐 1년 반, 1년 정도 겹치고 굉장히 이제 펀더멘탈 연구를 잘하시는 분이고 오늘 발표해 주실 내용은 디스틸레이션 쪽, 그 약간 티오리 쪽을 좀 이제 파본 그런 시간이 될 것 같습니다. 네, 박수 많이 하겠습니다.
뭐 한글로 해도 되나요? 영어로 해도 되나요?
영어가 편하신 영어로 해주셔도 되고요. 네, 우리 라디카도 있으니까 영어로 해주셔도 될 것 같습니다. 아니, 뭘로 하시면 상관없어요. 사실.
그래. 그러면 일단은 뭐 한국어로.
한글로 하세요.
Is Korean okay? English fine? English better or Korean is?
아니, 한글 하나도 못해서 나중에 배우고 싶으면 따로 영어를 얘기해줘야 돼가지고 이왕이면 영어로 하는 게 나을 거예요.
Okay, 그럼 영어. Okay. Then I'll just use English. Okay.
Okay.
All right, cool. So today I'm going to talk about the distillation. So basically the idea is that to understand why distillation works. Actually, maybe some of you are not very familiar with the distillation, so I will probably also cover that slightly, and then after that, our main paper, main topic for our paper is about why this kind of distillation works, and then how should we actually optimize the performance of this distillation in the end, basically. So this is in collaboration with my teammates in Google New York. So Aditya, Ankit, and Shashank, and then Sanjib. Sanjib is my manager. So and also here's a small picture of the base, because we will talk about base a lot in this talk. And also this is basically a kind of lantern to actually lighten the dark cave of the knowledge. So basically, when we talk about the distillation, we also talk about many of like basically the transferring the dark knowledge from a teacher. So I'll define the teacher and student in the later, basically. But basically, distillation is about how we actually transfer the knowledge from a very complex model to a simple model. That is basically the classic setting of distillation. Okay, and that is we believe that somehow the dark knowledge from a teacher is actually transferred to the student, and that is basically like this picture. So we enlighten some of the areas of data distribution from a teacher to student to help the student to learn about the data itself, right? So that is the picture, and so I'll probably just start with the what is actually the distillation, because well, this term and also this technology itself is very popular in industry in many various regions, and one of the reason is so we are training really large models, like really large models, like say that GPT-3 or like BERT models, and BERT large has like probably like 24 layers of transformers plus like 10K like hidden layers, and basically it is a gigantic model, right? So making an inference in this gigantic model takes a lot of time and also a lot of compute. That is very costly. So if you want to empower your like applications such as like mobile phones or like say the Google Photos or like many of these kind of products, you want to use those kind of very powerful models because they are accurate, right? Very accurate, like surprisingly accurate, and they are sometimes like surpasses the human human limits, right? So you want to use that, but it is very costly. So the way to use this model in many of these kind of production or kind of this kind of real world applications is you want to train a simple model that can mimic this behavior of these complex models. So that is why we are doing this distillation. So distillation is basically you want to transfer knowledge from a complex teacher to a simple student. That is a classical setting. I'm just saying this is a classical setting because that sometimes this is not exactly true. So you can sometimes train a teacher and train another teacher, and then you can distill from the same model to another, and that is called like this like war again setting. Well, there's some other literature about that, and there's some good theoretical like guarantee for this performance. But basically, there are many different settings But in classical setting, we usually like train a complex teacher and then distill it to the simpler student. And you also want to like think about why we are using the term distillation. So distillation is if you're like alcohol consumer, you know that when you brew the whiskeys, you distill it from some very kind of raw materials, right? You change the temperature of this alcohol, and then you really kind of distill something into something, right? So this term was actually, I think, introduced by Hinton. I think the name of the paper was knowledge distillation something something, and they use the temperature a lot, and that is actually quite essential piece to actually make the student perform well. And I'll also talk about that the connection between this temperature with our kind of the theoretical like understanding in the later. But basically, you want to kind of keep thinking why we are doing this, and then why this is helpful. Okay. And usually the setting is you train a teacher. So this is teacher, complex teacher from a label data. So you have X and Y. So you have some input and then some labels. And what we usually do is that for the field training, we can also use the label data, but we usually use some unlabeled data, and then use a teacher, this is a teacher, to actually estimate the Y, the label distribution from the teacher. So that's why we call PT, Y equal X. And then use this data to actually train the student, okay? So that is how we usually transfer the knowledge from the teacher to the student. Any questions? Okay, I'll just keep going.
When you say the temperature, what do you mean by temperature?
I'll define it
Okay.
in the next slide, okay? Yeah, so I think I already kind of covered that, but basically why we are doing this, I think why is really important in every research. You should always ask why. So why we are using this distillation is usually these reasons. So teacher models are teacher model is probably too heavy, like sometimes compute heavy. It takes a lot of time to make an inference, and also sometimes the model itself is too large. Like you can't really fit into the memory. So you want to do that. Of course, that there are really a lot of like research that kind of handles this like directly to actually change some modification to the teacher, such as like quantizations. Like you can quantize the like float vectors, like 32 float vectors into 8 bits, or like there are many things you can do actually to shrink the size and also speed up the inference speed. But distillation is also another way to actually handle this. Okay. And this is what I just mentioned, that there's another like variance that we just use the same student and teacher for the vulnerable again setting, and this is also quite helpful. And you can probably take a look at the the paper if you want. But there are like many different like settings basically. And this is the classic knowledge distillation, and I think this will answer your question about the temperature. So if you think about the distillation in the whiskey brewing process, you change the temperature to actually control how much alcohol you want to like pass from something to something, right? So here is also something called the temperature here, and this is how you generate the basically the student target from a teacher. So Zi and Zj are logits from the teacher, okay? And basically you predict something, some logic from the teacher, and then you divide by the temperature value, and then make a softmax to make actually the softened label. I'm calling it softened label because let's consider that you have a high value of temperature, okay? Let's say the 20, okay? Then logic will be very close to like 0, or basically the scale of the logic will be very close, right? When you do that, actually this softmax distribution will be softened. So when you actually have the opposite, so say that low temperature, let's say that like 0.1, okay? If you use 0.1, then all the, oops, why is it going on?
It's touching it.
Oh, that's nice. Okay, so when you do that, actually this scale will be higher, right? When you have a lower temperature, okay? Let's say 0.1, then like this logic will become like 10 times, right? in that case, the softmax, the distribution over the labels. So you know that this is basically the QIs are the probability for a label for all the labels, right? And this is normalized, right? And this will be sharpened when you have lower temperature. But when you have high temperature, this will be smoother. I want to draw it, but I think it's okay. Yeah. So basically, like this sharpen or like this, right? So when you do that, so when you have a high temperature, the QI become a softened target distribution, and the classic setting of the distillation from the Hinton paper is actually encouraging you to use the high temperature during the distillation process. And once you train everything, then you can set the low temperature after transfer. But yeah, you can also schedule it like accordingly during the training the phase or something like that. But basically, the idea is that you want to soften the label distribution during the training the student, and they're basically calling it in the Hinton paper. They want to do this because one, when you soften the distribution, you can actually pass more data from the teacher to student, right? So if you have very sharp label, such as let's say that you have like 1.0 for one label and all those zeros, right? You will just marking this class is really relevant and nothing else, right? But if you soften the labels like 0.8, 0.3, and something like that, not 0.3, 0.8 and 0.1 and something like that, and you're actually passing the knowledge of these two classes are actually confusing, right? So when you soften the labels, you are actually passing more knowledge from the teacher to student. So that's why they're doing the high temperature setting for the distillation. And we'll actually see exactly why this is actually helpful during the process. But in the Hinton paper, they're just calling it as a dark knowledge. Okay. Oh, this is nice. Okay. So let's define the knowledge distillation more formally. Okay. So we will have a lot of notation. Let's actually call this R hat, FMS, as the risk. R stands for risk. Okay. Risk of the this function, the predictor, and this is the set of data points actually. Okay. And this is basically empirical risk from the training, right? So we usually basically we want to minimize this one, right? So this is just the basically the arithmetic mean, the averaging, and then we have a loss, right? And we have the ground truth label, and f of xn is basically prediction from the model, okay? And we can actually write this down with some very kind of label-specific loss term here. And also this is one-hot encoding. So you can also think about this cross entropy term, right? And there's a 1 for the ground truth and 0 is otherwise, right? And then this will be kind of the low loss for that specific label, right? So this loss and this loss is slightly different because this is over all the label and also this has the ground truth term, and this is kind of this is the unwrapped version of that, and then there is a one-hot vector here. Okay, and distillation training loss, you can actually see that as a slight variant of this empirical loss, actually, right? So the R tilde is the risk for the distillation loss. It's actually using this right term is actually the same, but this is actually coming from the teacher, right? So this is the instead of using the one-hot vector, this is actually coming from the teacher, okay? So you can see there is a very similar kind of pattern here, right? So you have this term, the loss term for each label, right? And then you can either multiply it, actually this is not multiply, this is an inner product, right? So inner product with this one-hot encoding or this teacher distribution, right? So you can see this similarity, right? So, and actually, let's say as you think about how we measure this how we actually measure this population risk. So population risk, what I mean is that not the empirical risk, but the true risk. Like let's assume that you have a true distribution. Let's call this P star, X and Y, and we usually call it as a Bayes distribution. So because this is like basically the oracle knowledge or the optimal or the true, like from actually from the data, and we call it as a Bayes distribution. So when we actually have this, the true risk ROF is actually expectation of, this is a joint expectation, but this is kind of just unwrapped, like x and the y given x and for this, right? And if you think about this as a kind of very label specific loss term, this is nothing but just L of fx, which is the same the right term from the previous slide, and you basically inner product with this p star x, which is the ground truth label from the Bayes distribution. And this is exact risk, right? This is basically the exact risk. So this is the like what we want to have, right? And if you think about the empirical risk versus this risk, is empirical risk is basically what you observe from the data, right? And this risk is actually what you want, right? Sometimes the data itself is noisy, right? Noisy, or like you can sometimes have very partial observation, right? So for the some classes, you have two like small number of examples, and maybe the risk for that classes are inaccurate, right? But this one is basically what we want. Okay, and in this case, you can also notice that, so this is not using the 1/2, right? 1/2 is from the empirical risk, right? This is actually probably like not just 1.5, 1 and 0, right? This includes the whole distribution of the labels for that particular example X, right?
So is it across the labels, or is it just the data distribution? P star X. Is the probability of the likelihood of a specific sample?
Yeah. Well, this is for that the particular, like, this is label distribution for X example X.
It's a label distribution.
Label distribution, because that you want to like multiply with this loss for all the labels, right?
Okay.
Yeah. This is not just like X, like distribution of X, right? This is, you can probably write this as like Py given X, like something like that, star or something like that, but we are just kind of shortening it like this. But this is the label distribution for X. But this is coming from Bayes, okay? So, but you can just see that, well, in her tree, the real risk or the population risk is actually using the smoothed version of this one, right? So the Bayes optimal, or the optimal parameter, will be based on the Bayes probabilities using or basically using this kind of smoothed version, right? Then we can ask ourselves, what will be the kind of base these two training laws? So let's say the teacher is Bayes. We have perfect teacher. So whenever you ask X, you get perfect the label distribution. Okay, then we can actually substitute P star, but we PT of Xn with the P star. Right? This is coming from actual the Bayes distribution. Of course, we can't do this when we train, but let's assume that. Okay. In that case, we can actually prove that we are lowering the variance over the standard loss. So let's this is a kind of packed the formulation, but this essentially is quite simple. So let's consider these ones. So the variance of the Bayes risk and the variance of the empirical risk. So this is what we usually solving during the training, and this is what we can actually get from the Bayes distribution. Okay, and this is always true because we have a like short proof of that. But basically, the variance of the Bayes risk is always smaller than the variance of the empirical risk, which means that if we are minimizing the Bayes risk, the variance of our training loss or the model itself will be lower. So that means that we can actually achieve the more accurate model in the end, right? So that is basically why would we want to use the Bayes risk? Well, of course, we don't have the Bayes risk yet, but yeah, we want to use the Bayes risk instead of the empirical risk, which is the standard loss, right? And here's the short proof. Well, of course, that you can probably read the paper, and the paper has some more details. And I'll probably just pass it very quickly. But the left-hand side is the Bayes risk. So you have this and this, and this P star X is actually you can write it as a expectation of y given X, and then you have a variance. So variance is basically something expectation square minus something which is basically after. So you can see that the square is like the opposite, right? So this is how you can just derive the expectation. And right hand side, you just compute the variance of this one. So basically you have the square here inside, and the right hand side is like the same thing, right? So if you compare this one and this one, you can actually use this kind of the Jensen inequality, which is basically when you apply some function over expectation versus the other ones. This is basically the inequality you're getting. So basically, well, this I just rushed all the things, but basically what this is telling us is the base risk will be always smaller than this empirical risk. So you want to use actually the smoothed version of P star if you have any access to the P star, not the like 0 ones, right? So so you will start to ask that if you have a perfect teacher, so basically you can say this base the distribution is actually a perfect teacher, right? If you have some oracle that tell you like label distribution always accurately, then you have lower variance, which is good, right? But you don't have the perfect teacher, right? In that case, what happens with imperfect teacher? So teacher can make some issues, like some inaccurate ones, but basically what can happen, right? But yes.
Why is it important to use a lower variance risk instead of the standard loss?
Well, usually like when you are optimizing, well, basically the loss variance will tell you that how much like variance of performance that you will be getting during the training, right? So basically,
so it's a better estimator.
Yes, better estimator, basically, yeah. Okay. So if you use a better estimator during the training, well, you have higher chance to get a better model, right? Yeah. But well, basically that. Well, it is not always the case, but yeah, like basically in general, yes, like that. Yeah.
Okay.
Right. So so we now want to ask ourselves that what about like when we have the imperfect teacher? Okay. So let's actually consider this the gap between distillation risk and the population risk. Population risk is basically the base one, and the distillation risk is actually coming from the teacher, right? And then there's some derivation. Basically, when we compute this gap between these two risks, this is actually bounded by two things. I have some other slides to actually go over some of the details. But basically, the gap, expected gap between the distillation risk, which is coming from the teacher, and the population risk, actually this is coming from the base or the true population, is actually bounded by two things. And this is actually very similar to the bias variance trade-off. I think you know that the very classic setting of the bias variance trade-off, right? So when you have a complex model, you have a lower variance, but you have high variance but lower bias, right? You have a simple model, you have a high bias but lower variance, right? Usually that's the classic setting. And this is actually also, you can also like defactor this gap between the true risk with the empirical risk and the distillation risk similarly. So this term is divided by n, and then basically this is the variance of a loss from the teacher, right? So PT of this, basically this is the loss from the teacher, and there's a variance term, and plus basically this is how your prediction is close to the base. So there are two terms. One is bias term. So this will measure that, like basically how far your teacher is coming up from the true distribution of the labels. Okay, this is basically the bias of your model, and the first term is the variance of your model. So when you have a complex model, then the variance will be high, right? And then bias will be probably small, vice versa. So I'll go over some more details, but basically the gap between these two things are defined by two things: the bias and variance of the teacher. Okay. So and also this will tell you that, well, none of these terms are defined by the accuracy, right? So actually, there's nothing for the accuracy. This is not the accuracy. This is basically the log loss for the teacher, right? How the teacher is doing with the and how much variance that we are getting, and also this is how much we are accurate to estimate the label distribution, not the accuracy, right? So this will tell you that accurate model doesn't guarantee small gap between this distillation risk to the population risk. What we want to have is actually we want to minimize this term, right? Or this, right? So this will tell you that we want to train a teacher that actually accurately predict the labels, not the top one accuracy, right? You want to closely predict this label distribution when you can also tell this part as the mean squared error of the probability of the labels. And also you want to have a small variance. Well, basically there's a trade-off, right? So this is the proof. Well, I may not just go over all the details, but basically expectation of this is, well, you can call this as delta, and then this can be written like this, and then the third line is using the Cauchy-Schwarz inequality, using this kind of the inner product, and then this is kind of jointly, and this is always smaller. So this is basically the inner product. So you're getting the two terms, like L2 normal of this and L2 normal of this, and then you can also change this part with this the equivalency of norms. So L2 goes to the L infinite norm, and then you can have a scalar, and this is also true for the inequality. And then this part is always kind of bounded by some number, so you can probably ignore and then use this part, and yeah, basically all the hacks, but basically this will tell you that these bias variance are kind of defactored, and then we have inequality. And here are the more kind of high level thoughts. Probably this is the slide that you want to actually focus on. So basically the bound is bounded by two things, the n, and with this variance of the teacher, and the how teacher is closely accurately predict the label space, right? So we have three cases. One, when the n is large, this part will be going away, right? Because this is also like divided by n. So will basically this part, the teacher's bias is basically the limiting factor. So when we have small bias for the teacher, then you have a better estimate of this distillation risk, which give you the better performance for the student model, right? And when we have very complex teacher, this equals to the high variance. So this term will be very high, and then this actually may suffer. We can actually have a larger gap between the two things, and thus that will lead to the poor student performance. This is really important because, so let's consider that, I'll cover that later in some other figures. Basically, you want to maybe have very complex teacher to have a very accurate model, right? So maybe the accuracy of the teacher can be really high, but that is also very complex. That will increase this term, and actually that can lead to poorly performing the student. We sometimes call that as an overly confident teacher, because sometimes when your teacher is really confident and they're doing really well for the training model and also testing set, but sometimes their distribution is not very calibrated. In that case, since this is really high, and also probably this can be also not very good, in that case, actually when you distill a student from that teacher can actually lead to the poorer performance. I'll show some empirical results for that. So having very powerful teacher is not actually a kind of key to actually train a very successful student. What you want to do is actually you want to minimize this estimate, right? And also you want to use some probably simpler or kind of okay-ish teacher to actually lower this part as well.
Can't you use a very powerful teacher, but you can control the temperature afterwards?
Yes, exactly. So temperature is actually what you are doing. So temperature is actually can lower this part, right? Yeah. So exactly. So you can see that, well, in the Hinton's paper, they use temperature without knowing too much of this kind of theoretical background, but basically our kind of formulation shows that using the temperature will actually scale the confidence of each of the labels, and then here probably that is a good, more probably the accurate estimate of this base term, right? So you can actually lower this by using the high temperature. Yeah, and we expect that that's why using the high temperature was actually working really well in practice before. And also this third part is the boundaries itself is not based on the accuracy, right? There's no like accuracy term, right? So lowering this will be actually better. So basically when the label distribution from the teacher is well calibrated, which means that calibrated means that this is closer to the base distribution of the labels. In that case, that will actually work better in the distillation setting. Okay. So this is a kind of synthetic example. Well, basically, we constructed some label distribution from many teachers using this form. So actually, you can have this is the label, like synthetically generated from some arbitrary teacher using some bias term and some variance term, and then we just generate the data and then train a student to see how they're doing. And this is the main picture, one of the main features. So basically, the left line is the MSE, how we are far from the base distribution. So this is using the synthetic data, so we know how the data is generated. So we have base estimate, okay? And then we can also generate the PT from that setting, like by artificially generating bias and the variance, and then we measure that. And this is the performance of the student when we actually use this label generated from the teachers to actually train our student model. And you can say that when we actually have a higher MSE, the student performance is going down, right? Which is, well, basically telling us that, well, our bond is working nicely. And this is from actually the real world data, fashion MNIST. And I think in this case, instead of using this kind of artificial like alphas and betas, I think we use the depth of the teacher. So when we actually train the teacher, like CNN models, you can keep increasing the depth to actually make more complex model, right? So basically, if you do that, you can also measure this MSE from the teacher. And then we measure the accuracy that is actually trained from the teacher. And you can see that the performance actually goes down when we have a higher MSE, right? So basically, this tells you that, well, the accurate modeling of probabilities is actually really well correlated with this student performance in the end. So, and you can also see this is CPAR10. CPAR10 is the computer vision, really kind of popular computer vision classification. And then this is top 1 accuracy, and this is the depth of the teacher. So like usually CPAR10 use resonant architecture, right? So you can keep stacking this kind of resonant blocks, right? So like usually a 56 or something like that. But as we kind of varied from 8 to like 56. And when you have a higher depth of the accuracy will just keep growing up, right? But when you actually distill from this teacher to a student, actually, this is teacher depth. The student is fixed, okay? So when you actually train from the 14 depth teacher, actually the performance of the student is actually better. The best was achieved at the 14, right?
Is that the test accuracy? The top 1 accuracy?
Yes, top, yes, test accuracy. Oh. Yeah. And also, if you plot the log loss is basically the how you're close to this label distribution, right? And you can say that the teacher depth at 14 is actually the best. So basically, teacher is mostly closely predicting this label distribution at the 14, but it got worse when you have larger number of depths, right? So more complex teacher, basically.
How did you get the P star in the KO term?
So this is using just the test data. So this will not be really accurate. So this is not the MSE, but this is just log loss from the test set. Yeah, but we still get the lowest the log loss for 14 teacher. Depth 14 teacher.
So the teacher is also, you're also calculating KL for the teacher as well as the student, right?
Yes.
So in that case, when you're calculating KL for a teacher, then the teacher would be P hat on the right side of the KL term. In the y-axis.
In the y-axis.
In the y-axis, KL
Oh yeah,
P
yeah.
star P hat. So when you're calculating KL for teacher, then teacher would be P hat. So where would the P star come from?
Wait a second. So, yeah, I think we kind of estimate P star somehow. Yeah, actually, P hat is coming from the both of the teacher and student.
Right.
Yeah, yeah. And also P star, no, P hat is coming from either teacher or student.
Yeah.
And P star is actually, I think we estimate from the data. Yeah.
Okay.
Yeah. And this is using the calibration error. So this is an estimate of the how well the teacher is calibrated, but this doesn't show you that the dip here. But basically, when you have a more complex model, the teacher is actually like getting worse and worse in the calibration error, and somehow the students trained from the teacher 14 actually achieve the best calibration. It tells you that maybe this is why we are getting good performance. Okay, so temperature scaling, I think I mentioned it previously. So basically, usually the teacher models are highly complex, and they're optimized to maximum accuracy, and sometimes it often becomes very overly confident. So usually the prediction can be really concentrated in the one labels and nothing else, and that will actually have a can have a high MSE, which is the gap between the P star and then the PT, and increasing temperature actually can prevent that somehow. Yeah. So this is probably the why using the high temperature actually works nicely during this distillation process. Okay. And I think this is a kind of extra from the paper. So we actually wanted to apply this in the some of the information retrieval setting, and then we thought that this is also cool, so I kind of cover it shortly. So we can also think about that using this distillation in the softmax loss. So let's say that we have a when we want to distill the softmax cross entropy from one teacher to another, we can actually use this term here as a label, right? So this is what we already had before, and this term is just fixed. So basically, this is all the y's from the labels, and then there's ground truth, and then you want to measure the gap. So this is coming from the normalizer, from the softmax, right? So if you consider the softmax, you have a top term, which is basically this term, right? And then you have the normalizer for the older classes, right? So this term is actually coming from normalizers. So softmax is nothing but you have all the things, like basically you have a losses from all the other labels minus the positive one, right? And then this part is
like a max margin setting.
No, this is just softmax, but it's written in some like different way. Yeah. So yeah, log, and then you can actually, because the log, then you can actually.
Oh, okay. So
yeah.
the top
So it's the same thing, but we're writing in some
explanation.
Like, yeah.
Okay.
Yeah. So and this part is basically the label, right? And if you think about this, you are actually doing some kind of expectation, right? So you are going over all the labels, and then this label is just using the ground truth label, not the smoothed version. So and the label itself is using the smoothed version, but this part, like using the positive and the negatives, are not actually using the smoothed version, right? So we actually wanted to use the smoothed version for this part as well. So basically, we are weighting this term by the distribution. So you can think about this as a kind of expectation over all the labels from the one positive losses and to another ones. So this will weight the positive examples and negative examples in equally. And what we are doing here is we want to actually weight the positive label and the negative label by the label distribution from the teacher as well. So this part is coming from the teacher, and also we are weighting each of the label distribution with this some negative correlated version of this teacher. So when we when the teacher is confident, then we are waiting because this will be higher, right? So we are kind of waiting down, and when the teacher is high, the opposite, and this is basically the opposite. Yeah. So we apply this into the information retrieval setting. I think this is coming from Amazon 13K prediction or something like that. And this is teacher, and this is student that is solely trained. And then this is using the student plus just the distillation. And this is using the double distillation. Basically, we apply that weighting to the negative terms as well. And this was actually performing the best for the two cases. And actually, this is the end of the talk. And well, basically, I just want to summarize. So we talked about a lot of things. We talked about what is the distillation, right? And also we used to use these kind of high temperature and low temperature regime when we apply the distillation, right? And in this talk, we now understand why we are using this temperature thing. It is because that when we actually smooth the versions, smooth the teachers, this can be actually a better calibrated version of the teacher, right? That is why. And the reason why is basically when you do that, we are now getting closer to the base risk, right? Not the empirical risk. So that's why we want to do this kind of smoothing, or we want to actually use the kind of well-calibrated teacher. And also, the imperfect teacher can still give you the good performance as long as you have a lower variance and also lower bias when you're predicting this label distribution. And also, you want to note that more accurate teacher in terms of the top one accuracy doesn't really kind of sometimes doesn't really lead to the better student distillation. And also we certainly cover the double distillation for the retrieval, but I think this is probably kind of specific. So yeah, that is it. Any questions?
Yeah.